So I actually found the slide I was looking for. It was a different presentation. So just to give you the issues there are with okay, it doesn't seem to be working. Oh, it is. So this is your conceptual model of a shared memory system, that you have so we had 6 cores here. You have 6 CPU cores, 1 block of memory, and an interconnect. And I said that my mental model for this is 6 people in a shared office with a shared whiteboard. So so each process can access the memory, and that is true. Each process can access the memory, but in practice, it's more complicated than that. So under the hood, you may have multiple processors with their own memory, okay, but they're wired together in some way. So every process can access all the memory, but it's much quicker for this process to access this memory than to access that memory. And so in MPI, you never have a problem because each process has to access its own memory. So whenever they allocate memory, it's allocated in the correct place. The problem in OpenMP is that the master thread can allocate all the memory, and then later on it can be accessed by all the other threads. So when the master threads allocates memory, it will by default end up here. Then you do a parallel region. That shared array is accessed by all the CPU cores, and it's in the wrong place. So you have to do tricks to make sure that the memory is allocated in the correct place. And Linux doesn't, well, there isn't very little support in Linux for this to do it properly. You just have to do it yourself. So that was what I wanted to. That is what I wanted to show. So that was the slide I was looking for. Apologies, it was a bit late. And now I'll go back to the actual talk. So all my presentations closed when I. So this is where we got to before. Fine. So I will share this slide. Seems to be a delay. Okay, bit of a delay. There we are. So the styles of MPI+OpenMP, you can identify 4 basic styles of MPI plus OpenMP programming. And they get basically depending on when or how the OpenMP threads call the library calls, and each has advantages and disadvantages. And the MPI now does support threading, and at least it is aware of threading. So the MPI library may support threading. However, that's going to have some overheads. And you'd be a bit annoyed if you had a pure MPI code and tomorrow it started to go slower. And you ask the system administrator, why is my MPI code going slower? They say, well, we added a threading support to the MPI library. So, well, I don't want threading support. So what happens with MPI is now there's a separate initialization routine where you say, this is the level of threading support I need. And that allows MPI to map in the correct library. So you don't pay the overheads unless you want to. But the 4 styles are called master only. This is the default style, it's the simplest. All MPI communication takes place in the sequential part of the OpenMP program, no MPI in parallel regions. And that's the simplest model. What that means is you communicate between nodes in the normal way from thread 0, the master, the controller process. And then all your OpenMP does is it speeds up the calculation. So you have serial and parallel regions, and in some sense, the parallel regions just make the calculation go faster, and you do all the communication in the serial region. And that doesn't require any extra functionality in the MPI library. The next one is funneled. It's similar, that all MPI communications takes place through the same controller thread 0, but it can be inside parallel regions. And so in this model, you're using threading, you're calling MPI from parallel regions, but it's up to you to make sure that only one thread calls them. So you basically have to, you're guaranteeing to the MPI library, look, I'm going to be calling the MPI library from parallel regions, but only the same thread will ever call that. Serialized is slightly different. What you're telling the MPI library there is, I am going to make MPI calls from parallel regions, but only one thread will make MPI calls at any one time. I will make sure that and in all these models so far, the MPI library doesn't have to do much because it's never being called twice at the same time. You, as the user, it's up to you to make sure that you're calling it. The only issue there is it can be a bit difficult here because what you want to do there is you might want to send a message from thread 1 on rank 0 to thread 3 on rank 1. Okay, you've got multiple threads. MPI doesn't send messages between threads, it sends messages between processes. And so you're going to have to some way of making sure, look, you're sending a message to rank 1, but you need to tell rank 1, by the way, this message is for thread 7. And the obvious way to do that is through tags. You tag the messages with the thread number, but there is no, well, there is, very recently MPI, there's some support, but there's starting to be no support for that. The one where the MPI library has to do a lot of work and which will probably incur overheads is multiple. MPI communications simultaneously in more than one thread. You can create a parallel region and any of those threads can call the MPI library at any time. Now, some MPI implementations don't support this, and those which don't do very well. Possibly all they've done in the MPI library is put locks, mutexes around all the critical points. I don't know. If we designed MPI today, it would be designed as being thread safe from the start, but it wasn't. It was designed 30 years ago, and that's why we run into all these problems. So master only is very simple. You have explicitly parallel regions, OMP parallel, where you do some work, and then you do all the communications in a serial region. So the parallel region ends here. So in this region, it's a fork join model. You've only got a single process running the master thread 0, and then you have work again. And that's very, very simple to do, and it just involves basically going to your MPI code and speeding up the work regions with parallel directives. Funneled is similar, except the MPI communications can take place within a parallel region. And so what you do is you make sure that if you didn't have this master here, all the threads, you'd spawn, say, 10 threads here, all of them would call the send routine. You don't want that. You want it to happen from a single thread, the master. So there's a pragma in OpenMP, OMP master, which says only the master thread does this. However, presumably the work here is updating some data which you're sending. So you need to make sure that the work is finished before you issue the send. That means you have to have a barrier before to make sure that this work is finished. It's starting to get more complicated. You need a barrier here to make sure that all the work is finished, and you need a barrier afterwards because you don't want to update these send buffers until the send is complete. And master doesn't have a barrier. So although it looks very simple, you just make sure that all the MPI communications takes place from a master thread with a pragma OMP master, same in Fortran. It is slightly more complicated because to avoid race conditions, to avoid multiple threads updating that you need to stop any of the other threads touching that buffer while the communications is taking place. So you need here a barrier before and after. So it is, now you didn't need that in this model because effectively the end of the parallel region is a barrier. All the threads wait and come together and you only have a master thread. In this model, all the threads are still running, so you need to make sure that they don't do anything until you're ready for them. Serialized says only multiple threads will be calling the MPI library, but only one will call them at once. And that is called critical. The way to do that in OpenMP is critical says only one thread can be in this section of code at any one time. Okay? So that means that basically, only one thread is in here at any one time. So this pragma will serial. So you won't, the threads will call the MPI library sequentially one after another in an undefined order. Is a first come first served model, but it does achieve what you promised to the MPI library, that only a single thread will ever call the MPI library at one time. So this is sort of similar to the previous one. However, multiple is the one where you basically say, look, I will have any thread will call the library at any time. I do work, I do an MPI send, I do some other work, and it's you, the MPI library's job to make sure that that doesn't, there's no conflicts there. So indefinitely this model, and I don't think in this model, but definitely in the multiple model, the MPI library has to be thread safe. It has to worry that it has some data structures, they might be updated by 2 threads at once. So making MPI libraries thread safe is difficult. The simplest way, you either have multiple data structures, 1 per thread, or you lock the access to the data structures. But both of these add significant overheads, which would hamper single-threaded codes. And as I mentioned earlier, to avoid that being a global hit to all MPI programs, MPI defines various classes of thread usage. And this is an MPI init thread. So you have a separate new routine called MPI init thread. So what you do is you say, when you call MPI init thread, it's the usual argc or argv, or you can specify null here. But you specify a thread level which is required, and we'll come say what they are, but you get back a provided. So what you say to the MPI library is, I would like MPI thread multiple, and it will tell you whether it can do that. And if it can't, it may not return multiple. It will say, I can only do serialized. I might ask for serialized, and it says I can only do funneled. So it's up to you to check that when you request a required level of MPI, of threading support, that when MPI tells you what it can do, it has given you that. So if you get a lower level of thread support than you want, either you have to revert to a simpler hybrid MPI OpenMP implementation, or you have to print, look, I can't do it. I require MPI thread multiple, but you cannot provide it. So it is slightly tricky, but the reason that there is a separate initialization routine, as I said, is so that you don't pay the overheads of the MPI library unless you really need them. So the 4 models are MPI thread single, only 1 thread will execute; MPI thread funneled, as we saw, the process may be multi-threaded, but only the main thread will make MPI calls. We funnel all, so we route all MPI calls through the main thread, which is thread 0. We could do that with #pragma OMP master. I think they've renamed master now. I think it's called primary, I think. But I haven't quite kept up with the times. MPI thread serialized, so we said the process may be multi-threaded, and multiple threads may make MPI calls, but only 1 at a time. MPI calls are not made concurrently from 2 distinct threads in the same process. So that's serialized with the American spelling. MPI thread multiple is all bets are off, and you're saying it's the MPI library's job to sort that out. So now these thread values are monotonic. You don't know what they are, but the values are increasing. So when you get back required, when you get back provided, you see if provided is less than required, then there's a problem. Okay, so these don't actually map directly onto the 4 MPI OpenMP styles, because they're actually more general. As I said, MPI is designed to work with thread encodes, which could be POSIX threads. We're using OpenMP, so there's not a one-to-one correspondence. So for example, there's no difference between master only and funneled in the in this thing. Okay, there's no funneled and so we identified 4 threading styles, which are master only, funneled, serialized, and multiple. But in MPI speak, they both map to funneled. Okay, that's because, but it doesn't really matter. Only the MPI, only the main thread will call MPI functions. But if you just want to do MPI and there is no threading, you would call MPI thread single. To be honest, so technically, anyway, I wouldn't call MPI init thread with the MPI init single. I would MPI thread single. I would just call MPI init in the old-fashioned. But there you go. So yeah, you need to look at the MPI standard for details, but that's the idea. So there are various query functions. You can query the current level of support. So basically, MPI query thread isn't provided. You can say if provided REST request, you can abort. But you get that back at initialization time. So I think you should probably check at initialization time, not later on. So what are the advantages what are the issues with these four styles of MPI programming, of OpenMP programming? Well, clearly master only is simpler to write and maintain. All you're doing is accelerating the calculation phase with threading. There's a clear separation between outer and inner levels parallelism. The outer level is MPI, where you do all the communication, and then you have an inner level which has no communication, and you just do accelerate the calculation. There are no concerns about synchronizing threads before or after sending the messages, so you don't have to worry about putting in barriers and such like. The threads must have synchronized because they have joined together. So that is by far, and that is really what I would expect you to do in the traffic model. Disadvantages are, as we mentioned before, threads other than the master thread are idle during MPI calls. We haven't talked about caching very much, but if you understand the way that modern computers work, all the communicated data passes through the cache where the master thread is executing. So the data may be cached, your send buffer may be cached on the different CPU cores because it's being created or worked on by the different threads. But then when you communicate the data, it's all read onto thread 0, which means that your cache locality is not good. Also, there's no overlapping between inter-process and inter-thread communications. So basically, the inter-thread communications is done via OpenMP, the inter-process is done via MPI, and they happen in distinct phases. There's no overlap between them. And so you're not exploiting the fact that you could actually be doing communication between threads at the same time as doing communication between processes. The synchronization is done by parallel regions, which have a relatively high overhead. Modern OpenMP implementations are pretty good at keeping threads running, but there is an overhead to spawning, to forking and joining threads, spawning and ending a parallel region. And a technicality, but the MPI library is running in serial, so any work it does, like packing and unpacking of data, is done sequentially. But it is a very, very simple way to program, and the way that most people will do hybrid codes. So this would give the advantages of, for example, saving memory or additional levels of parallelism for the slab versus pencil decomposition. You could do all that with master only. So this is a simple example, that's slightly contrived, but we update A. Oops, sorry. We update A. We send A and we receive A, and we then update D. And at least in principle, okay, the send of A and the receive of A, it can be, we're doing a halo exchange here. The internode messages can be overlapped with the internode. So you're doing communication internode and intranode using MPI, and in principle they can happen at the same time. However, once you've accelerated these with OpenMP, okay, then the inter-thread communication happens. Whoops, happens here, okay, where you're accessing different values of A, and the internode messages aren't overlapped. So there's also an implicit barrier here at the end of the parallel do. So as I said, it's a very simple model, but you might be concerned that you're not making the most of the capability. Funneled advantage is relatively simple to write and maintain. There are cheaper ways. You have cheaper ways to synchronize threads before and after message transfers, like you can use a barrier, as we saw, which will have less an overhead than actually forking and joining the threads. And while the master thread is an MPI call, we just used a barrier, but the other threads could do computation. So you could, rather than doing a barrier MPI barrier, you could do barrier. Then, if I'm thread 0, sorry, but rather than barrier master barrier, you could do barrier. If I'm thread 0, call MPI, else go away and do other computation. So at least in principle, it's possible for other threads to compute while the master is in an MPI call. The disadvantages are, so actually what you can do here, if you're really brave, is you can actually you could nominate a thread to just do MPI. So you could say I've got 128 threads on my node. I will nominate one thread, let's call it thread 0, to do the communications, and all the other threads will do calculation. And then you can genuinely overlap communications and calculation because separate threads are doing them. Now that is quite tricky to do, but it is an option. The disadvantages are it's more complicated. There's an overlapping between these two outer and inner levels of parallelism. Still, all communicated data passes through the cache with the master threads executing. And still, well, inter-process and inter-thread communications still do not overlap unless you do this trick of actually nominating a process which does nothing but communication. So OpenMP funneled with overlapping, as I said, OMP bar work. Now we have if OMP thread number equals 0 to ascend, else do some computation. The problem here is the computation, you can't use work sharing. If you use OMP parallel 4, OMP 4, that will try and distribute the work over all the available threads, but you explicitly don't want to, thread 0 to do anything here. So you have to do the work sharing by hand, compute iStart and iStop indices, which is awkward. So you lose a lot of the benefits of OpenMP if you do that. If you do overlapping, okay, then you can well, you can actually, okay, so you can use the OMP parallel if you use nested parallelism. This is quite, well, I've never done this in practice, but it is possible in OpenMP to do nested parallelism. So OMP parallel, as written here, will spawn, if I'm on, let's say, 128 processes, sorry, CPU cores, will spawn 128 threads. What you can do is tell OpenMP just to spawn 2 threads here, okay? So this spawns 2 threads, and then this parallel region will spawn the remaining will spawn the remaining 127. And so this is called nested parallelism, but that has an overhead in the runtime. It's more complicated. It's harder to it becomes quite tricky if you do that. So I was wrong to say you can't use a work sharing in this model, but you have to use nested parallelism, which has its own overheads. So serialized, so that's fun. Serialized advantage is easier for other threads to compute while one is in an MPI call. And you can arrange for threads to communicate their own data. So we don't have this cache locality problem. You can say, look, if I'm working on some data and it's cached locally, I can do the communications for that data, and that's good. Disadvantage is getting even harder to write and maintain. You're getting more smaller messages are sent, incurring additional latency. So one of the advantages of the simple models is that you have a small number of large messages rather than a large number of small messages. And you need to differentiate. You will have multiple threads sending and receiving, and you need to distinguish between them. And so you need to not just say, I want to send this message to rank 5. I want to send this message to thread 7 on rank 5. And the easiest, you have to then, probably tagging is the best way to do that. You tag the message with the thread ID of who it's meant for, and that can become quite complicated. So again, to distinguish between threads, by default, an MPI receive, by any thread in the MPI process will match an incoming message from the sender, but we want to have different messages going to different threads. And so you want to use tags. If you're already using tags for some other purposes, it gets messy. So, you know, if you already tagged things 1, 2, 3, 4, 5, 6, 7, you might have to tag them 71, 72, 73, 74, 75, 76, 77, but the 70 means process thread 7. You have to encode 2 things in the tag. One is the destination thread, and the other is its original message. You can use different communicators. So if thread 0 only communicates with thread 0, thread 1 only with thread 1, thread 2 only with thread 2, you can create communicators, separate communicators which actually contain only those threads. That is quite elegant, but if you have more complicated patterns, it can get messy. So if you have a strict kind of differentiation of different thread 0 on rank, thread 0 only communicates with thread 0 on all the other ranks, and similarly for the other threads, then this can be a more elegant way of doing it. Multiple, the advantage are messages from different threads can in theory overlap, but in practice, many implementations don't do that. They weren't written with threading in mind, so internally they will sequentialize, serialize. You have this natural thing that threads communicate their own data, which is nice. And you have fewer concerns about synchronizing threads. You've kind of offloaded that responsibility to the MPI library. However, the MPI library may not be able to do as good a job as you know what your synchronization requirements are and it can implement them in a minimal way. The MPI library has to cope with all synchronization possibilities and maybe has to be more conservative. Disadvantage, it's hard to write and maintain. You can get lots of complicated race conditions and runtime issues. Not all MPI implementations support this. If you ask for MPI thread multiple, it may say I can't do that and return a lower thread level of threading than that. So you get a loss of portability. And most MPI implementations don't perform well like this. I mean, but the most crude way of making your MPI library thread safe is just to lock everything, and there you're just basically serializing things. So this is the way you might like the program in the most general way, but it does have quite a few issues. So the summary, MPI and OpenMP program is becoming standard practice. There was a study done on ARCHER which said about 30% of the consumed CPU hours on ARCHER used MPI plus OpenMP. I don't know if that's strictly true. 30% of the consumed hours on ARCHER used codes which supported MPI and OpenMP. Whether that means that people were utilizing it is another question. I'm not convinced that that's as high a level as you might think. Many people see it as the key to exascale because people are saying, look, we're going to have 256, 512 CPU cores on a node. It's mad to run that many MPI processes. However, to take full advantage of that, you would have to use MPI thread multiple. And that, again, means you need a very good MPI library. Correctness is hard. You have to consider race conditions on message buffers. Whenever you're sending a message, you have to worry that it's been updated by multiple threads. The achievement performance is hard. As I keep saying, the entire application must be threaded efficiently. And then even once you've written it, you have to optimize for two things, the number of processors and threads. We still have this, do you want to run one processor 128 threads, two processors and 64 threads each, all the way down to 64 processors and 2 threads each. And you get very slightly complicated issues between placement of processors and threads on NUMA architectures. So if I go back to this example here, the easiest way to eliminate the possibility of data ending up on the wrong NUMA region, on the wrong CPU, is to not run one MPI process and 4 threads, but to run 2 MPI processes, one here and one here, and each of those has 2 threads. That means the data will always be in the right place, okay? Because the MPI processes are running on separate memory regions. However, you then have to tell to your batch system or your runtime system, look, I've got 2 MPI processes. I don't want them here and here. I want the first MPI process here, the second MPI process here. And then subsequently, when you spawn your parallel regions, you have to make sure that the thread from this process ends up here and here. And that is complicated and messy and non-standard. It can be done, but it's yet another step you have to go through, which is complicated. If you get it wrong, your performance may be terrible. Seems to be a big delay in the. So the summary is, I would always say, think carefully before embarking on a hybrid solution. Why do you expect it to go faster? But if you have convincing reasons, you might want to do it. Remember Amdahl's law. Just because your kernel goes faster doesn't mean your entire code will, because if you use hybrid MPI, OpenMP programming in your kernel, then the rest of the code is running on fewer MPI processes than CPU cores. You may have written, depending on how you've written your code, this may be easy. You may be able to introduce OpenMP at a higher level, but if you're doing loop-by-loop parallelization, which is really the sort of standard model for OpenMP, that gives you issues. even if you've given so even if someone says to you, you're using a package, GROMACS, for example, it's a big molecular dynamics code, they might say, we have a very efficient Hydra MPI OpenMP, or in their case, MPI and threading. I don't think they use OpenMP model. Achieving performance, even with a well-written code, is difficult because of this process and thread placement issues with system-specific flags and settings, so it can be hard. So if I go back, so I was kind of imagine we wanted a shared data structure on each node. In MPI plus Open, so in the MPI model, we have a copy of each data structure on each node, on each process, which might be wasteful. In MPI plus OpenMP, we have one copy of the data structure on thread 0, but we can access it in parallel regions because we can declare it's a shared array. What would be nice, though, would be not to have to do all this, but just to be able to do this and have these MPI processes accessing directly the memory of this process without having to send messages. Now, that is not possible in standard MPI, but there is a special way of doing it. So you have two options to access these shared arrays. One is use OpenMP, make it a shared array within the parallel regions. The alternative, which is simpler, I think, because you don't have to introduce OpenMP, is to make any arrays declared on rank 0 accessible directly to the other processes, which requires some special memory allocation technologies, which we'll cover after the lunch break. So that's what we're going to cover after the lunch break. We're going to be doing something similar, shared memory programming, but doing it using purely processes. So that's really the exercise. I will show you. I now need to log on. Apologies, all my windows closed when my machine rebooted, so I'm going to have to take a second. So I will share this screen and show you how the exercise works. Okay. Well, I called it day 2. So you'll see there is a directory, for example, it's called C hybrid. In there is just an ARCHER2.job, because in fact, I would like you to write this code yourself. I'll maybe show you how to do it at the end. But basically, all you have to do is in the MPI code, copy the OpenMP directives from the OpenMP code into the MPI code. It's about half a dozen lines, and that's you done. Okay. However, the difficulty is at runtime placing these processes correctly. So what I've done is I've given you a script here which will at least help you do that, and you do that through a function called a test program called xthigh. This is something which Cray wrote, which basically does nothing but print out where the processes are running. So let's go through this. Okay, I'm running on 2 nodes. I'm running 32 tasks per node. That means a total of 64 MPI tasks. But that means I have got 32 MPI processes on each node. However, by default, those 32 MPI processes will be on the first 32 cores, but we want to be spread out every 4th core and fill up the gaps with the OpenMP threads. And that's what this incantation does, CPUs per task. That says allocate 4 CPUs, 4 physical cores to each MPI process, spread them apart. Fine, so that puts our MPI processes hopefully in the correct place. How do we make sure that the OpenMP processes are in the right place? Well, we first of all have to launch 4 OpenMP processes, and that 4 has to be the same as this 4. We've reserved 4 CPUs for each MPI process. We need to therefore spawn 4 threads for each MPI process. And this is a magic directive to OpenMP saying, could you please place the threads in the correct place. So I couldn't tell you that this actually is correct, but if you run the XT-High program, which is a module, all it does is print out, where they're placed. So when you're playing around with process and thread placement, don't do it with your application code. Just do it with XT-High. So let's just run that sbatch ARCHER2. It's all going to run in the short queue, but hopefully that's going to be relatively quick. It's pending. It's running now. And we can look at the output. Okay. Okay, so something has gone wrong here. So this is from the the previous run of the course, and I think things have changed. I should have so let me. Okay, I don't understand why. Okay. I don't understand what's going on here. Apologies. I thought this worked. What's it doing? Oh. Apologies. I understand. Sorry. The module system has changed, and in the old days, -s meant silent. That is no longer the right option. I'm sorry about that. So I'm going to have to change that. I'm going to have to change that in the. If you use this, you're going to have to change that module load command to module -s used to mean silent. Clearly, the new module command doesn't support that. Apologies for that. Okay, this is better. Okay, so let's move that up to here. That looks in the right place. So node summary, 2 nodes, 64 ranks. Node 0 is this is called node 5256. It has 32 MPI processes and 4 OpenMP processes, and node 1 is a different node. And then if we look, node 0 has rank 0, thread 0 on affinity is what CPU core is running on 0. So these are all correct. If you look, they all go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's fine. That's what we want. They should go all the way up to 1, 2, 8, and then back onto node 1. So what happens if we get things wrong? I can't quite remember how this works, but let's, for example, omit this and make this 1, which is wrong, but let's do that. Let's see what that does. So we haven't told MPI to leave a gap of 4 between all the cores. So what happens if we do that? Three, 7, 5, 7. Okay, so we're getting a warning here, saying, look, that there's something wrong here. The runtime system is saying that you were oversubscribing the processes. But if we go back, we'll see what happens here. That basically, rank 0, thread 0 is on CPU core 0. All the threads are ending up on the same CPU core. And that's not, so in fact, we're only using 32 of the CPU cores here. If we go down and then onto the next node. So if you get that wrong, you'll get massive slowdown. The other thing you might forget to do, I'm quite sure what the, whoops. the other thing you might forget to do is you might have that set correctly, but what happens if we don't have this magic indentation here? So you can see this is getting tricky and error prone, and this will be different on different systems. So this is this is not yet standardized, unfortunately. So what happened here? Again, has this worked? Oh, this has worked. Okay, so this is okay. We're okay here. Yeah. Okay. So you don't need that option on ARCHER2 on some systems. So without that option, it does the right thing. I would still leave it in because you can look up. So there is OpenMP. Not only has OpenMP has been extended recently to have environment variable specified thread placement, but I would always do that. But you seem to be lucky that it worked. So that's really what I will do. Is that what I will do is we'll do this exercise for half an hour. Whoops a daisy. So you may do this yourself, but I'll demonstrate parallelization. Parallelization. So that's what I'm going to do. For some reason, it's not expanding the text. Don't understand why. Yeah. So that's my plan. There's a practical session where I'd like you to play around with. There's exercise in the sheet, but just to finalize the day from 12:45 to 1, I will demonstrate how to do the parallelization model. If I can type with a live coding session, okay? I'll just do that with that. And I'm online now if you have any questions, but I'll mute myself and so I'll see you guys again in half an hour when I'll go through the exercise live. But please ask questions if you have anything. Okay, so I wanted to basically go through the solution. If anyone has any questions. So what I would do is I would basically, oh, I'm not showing the right window. Okay, so I would actually go, I'll do the C one for the sake of argument. I would go into the C MPI one, and what I would do is I would so I would take the MPI one, which is up there, and just put in the OpenMP. So we have to put in OMP. we now have to put this in, which is the print. We should always print out let's indent this properly. Okay. Now I'm going with the copy back, which is here. That's simply on this copy back stage. And now we have to find trafficlib.c. So where's trafficlib? Okay. It's really as simple as that, I think. So, and we now have to basically turn on OpenMP. So we have fopenmp, which is the way of turning it on. And we should be able to make, let's see if this actually works. It's okay, something funny is going on. I don't understand what is going on. Okay, sorry about that. Something very strange is going on ARCHER2. Do it by hand. How do I do this? Okay, there's something wrong with the file system. That's what's going on. Oh dear. Okay. I will try and log in again because possibly it could be this particular login node that's having problems. Okay. So what am I on here? Okay. How do I log on to a specific login node, William? Or actually, if you tried a different, I'm on login 1. Okay, so it's not the login node because I'm on login 1. Okay.
Yeah, I'm just on login 3 by default. You should be able to just SSH between them, but I guess only if you can get on in the first place.
So okay, so apologies for that. I'm not going to be able to do the demo. So okay, that's unlucky. Archer is going. Okay, so I'll do it in the lunch break to show you the results. What I was going to do was just compile that. Oh, I'm on now. Oh, okay, right. Right. So there was a problem here because actually, if you look in trafficlib in the update road, no, it's not there. I think I maybe didn't even say, okay. The variables names are different in so the mistake I made was No. What did it complain about? Sorry, apologies. I'm being an idiot. In the OMP parallel, in the OpenMP version, the loop is 1 to less to n cell, but here it's n local. So I have to change that to be this loop here is over n local now. That was my mistake. Okay, that should be okay. We do MPI ARCHER2.job / ARCHER2 what's called hybrid.job. We don't need XT high. And let's do let's run on 4 nodes. Let's do a big simulation. And again, with all my windows closed, unfortunately, I don't have immediate access to the. I should find in a second. There we go. So that should sbatch ARCHER2 hybrid.job pending, still pending. I wonder if there's a, oh, it is running. Okay. And I've got the wrong job name. I'm gonna have all these stupid prints here. I'm gonna have to get rid of that. Okay, so there we go. It ran 128 processes, 4 threads, and it got the right answer. Okay, so what I should do now, I will just get rid of those stupid prints. Get rid of that. What I would actually do is we now have to do, so you maybe don't want to watch, I'll show these hybrid. I'm going to basically go through all the, and that the way to treat I can do slurm tasks per node, I think is the way I can set that automatically to that is the way to do it. And then I can just go through all these permutations. So this is, I would of course put this in a script, but I'm going to do it by hand. So I'm just basically let's check that ran on 1 thread. Oh, that's really annoying. Okay. I've just done some very stupid things. Doesn't seem to be, okay, it's running again. Doesn't seem to be running, being very happy. So I should have got rid of that, but I forgot. Okay, I've messed this up. I'll do this offline and then get back to you. But that's the basic idea, and the code will work. It's just I'm getting my script incorrect. I think I'm probably this. It's not tasks per node. CPUs per task is what I meant there. That was that was stupid of me. Let's just check that works. So 93726. Okay, that's why it's running so slow, because I messed up the if you get the CPU allocation wrong, it's running. It should be running now. Fine, this will run in a reasonable amount of time. So we want the 2.6 is the one we're okay. This is the one we want. Okay, so that did run. That's correct, and it ran on. Yeah, so I will basically. Yeah. So it ran correctly, but it didn't do particularly brilliant performance. You can see that that's the way you do it. So there's a code that does hybrid MPI+OpenMP, 256 processes, 2 threads, and it gets the correct answer. But the performance is poor, and that's actually due to process and thread placement, to do with more complicated NUMA effects, which I don't have time to go into. But I will try and get some data for that over lunchtime. So the idea now is that we're going to come back. It's lunch break now, and we come back at lunch now, and then come back after lunch, and I'll go through the final. I should maybe present these. I'll try and get some results for this. But that's okay. So thanks, and speak to you at see you again at 2 o'clock after our lunch break.